is not calculus, but I'll give you a week, throughout the week you can be thinking about this one. This is slightly different than maybe the one you did a couple years ago in Algebra 2. So you come to a fork in the road, and you know that one fork leads to paradise and the other leads to the land of misery, but you're not sure which fork goes to which place, okay? Two guards stand at the fork, and you know that one of the guards always tells the truth and the other always lies, but again, you're not sure which is which. So the question is, you have permission to ask one guard one question, but that's it. What question can you ask to ensure that you end up in paradise? Okay. Have you heard this one before, Caleb? Yeah. Okay. I'm going to give these guys a chance to think about it a little bit. Yeah, this is a slightly different variation on the one that maybe you're used to.
Is one of the guards from misery and the other one's from paradise, or are they just?
Presumably one's from each, but that's not even really important. But I'll tell you this, they do know which road leads to which city, okay? Okay, I'll let you think about that. Any questions? Okay, all right. So for today, we get to start something really cool today. And this is going to look an awful lot like the stuff we just, in fact, it is. This is exactly like the stuff we've been doing, like the finding maxima and minima and inflection points and all that. Only the math is going to be a lot easier. This is just an application of that process, right? So did we get through everything on? I got to make sure we did. Gosh, you know what occurs to me? We may not have finished everything. Okay, so I think we'll start this, but I want to make sure that there's not one last problem hanging out there that we didn't do from before. We didn't do a trig function. That's the one we're missing. Yeah. So I do want to do one more. Before we join, I'm just chomping at the bit to get into this new stuff, but I know that I think we had one more thing we were still working on. Oops. Okay, we finished that up. Yeah, I think we had to do a trig function. I think that was it. Okay, we finished him up. Oh, okay, I remember I had kind of screwed this up a little bit. Okay, yeah, let's review what we had done on this. I want to make sure that we get this right. So we had this function, 3x to the 2/3 minus x squared, and we were supposed to analyze this function using tables, find everything, right? So we took the first derivative, we took the second derivative. You guys told me a bunch of stuff. You told me that the first derivative, which was equal to this row right here, equaled 0 when, what did we get for our critical number? When x equaled plus or minus 1, what we got to, right? So that was our first derivative critical number. We set the second derivative equal to 0, and we got x equaled plus or minus 1/3 to the 3/4, which we'll just make a decimal. So roughly plus or minus 0.439. Okay, and we were able to build a table from that. Okay, I think we looked at some symmetry stuff too, but I'm gonna not spend any time on that. So we're able to fill in our table here. First derivative critical number, so we know the first derivative equaled 0 at 1 and -1, and the second derivative equaled 0 at plus or minus 0.439 approximately. okay? We wanted to analyze this function. And here's where I think I really messed you guys up. Johan clued me into what at the end of the class, what I had done wrong here. I don't know what I was thinking. I was looking at the wrong row or something, but I plugged the wrong number into the wrong column. So let's go back a little bit. And I don't know why I was doing that. Let's go back a little bit and let's analyze this thing. What are we going to logically do to fill in our table here? Right? And this is a question of, are we going to use the first derivative test or the second derivative test to figure out what's going on at our critical numbers? We had two critical numbers, -1 and 1. What do you think? Should we use the first derivative test or the second derivative test? First derivative test, remember, I know it's been a week, right? First derivative test just means we're going to pick test points on either side of our critical number and see what the sign of the first derivative is. And that'll tell us if we've got a minimum or a maximum, right? We could do that, but we've already gone through the hassle of calculating the second derivative, right? So we might as well use the second derivative test. So at our first derivative critical number, we just need to determine what's the sign of the second derivative, because the second derivative is not 0 and it exists. Does that make sense? It would fail. If the second derivative were also equal to 0, then the second derivative test fails there. It doesn't have a sign, right? Or if the second derivative didn't exist at this critical number, then it would fail also. But we can evaluate the second derivative at 1. That's all we've got to do, is evaluate the sign of the second derivative at 1. So what do I get? If I plug 1 in for x, am I going to get a negative or a positive second derivative? I've got -2 times this factor here. What am I going to get? I got two factors. One of them is constant and negative. What's the sign of that factor going to be if I plug 1 in for x? Positive, right? Everybody agree? Positive. So I get negative times, they messed up my board over break. They did something to try to fix it and they thoroughly broke it. So negative times positive is negative, right? I get a negative second derivative. A 0 first derivative just means horizontal tangent, right? So negative second derivative then. Negative second derivative means concave down, right? So then we know it's a maximum, right? And we know negative second derivative. If the second derivative is negative, the function's sad, so it's frowning, and so it's a max. What about at -1? I could do the same thing. I know I've got a 0 first derivative, so I know this is a horizontal tangent line. I would just have to evaluate my second derivative at -1, and what am I going to get? Well, I get negative. If I plug -1 in for x here, what's going to happen to x to the 4/3 if I plug in -1? Keeping in mind that that's a 4. Think what that means. X to the 4/3 is the cube root of x to the 4th power, right? If I'm taking it to an even power, if the numerator of the fraction's even, what's the sign guaranteed to be? It's got to be positive, doesn't it? So I'm going to get negative times positive again. And so a negative second derivative is giving me my maximum again, okay? Okay, that's kind of nice. I almost know what's going on with the second derivative now too. Look, I know to the left of this 0 of the second derivative, I've got negative second derivative. To the right of this 0, I've got negative. What's the only thing I've got to do now to figure out if these are inflection points? What's the only thing I've got to do? Test a point in between. What point should I test? 0. Why not? 0 is the easiest point to test, right? So if we go up to our second derivative and we evaluate this thing, well, What's the problem there? Undefined, yeah. In fact, did we talk about this? Did we get a critical number for the first derivative there? We must have. Those are, okay, we found the zeros. I think that's where we left off. Y prime equals 0 when x equals plus or minus 1. Are there any places where our first derivative is undefined? Look at our first derivative function up here. So we're filling in our table. We've already filled in a lot, right? We filled in all this stuff, okay? Let's go back, though. Are there any places where our first derivative is undefined? Here's our first derivative written with positive powers of x. 2 divided by x to the 1/3 minus 2x. Any red flags go up there? Yeah, I'm dividing by x to the 1/3, right? So what value would have to be excluded? What value would make the first derivative undefined? 0, right? Because look, I've got an x on the bottom and I can't divide by 0. Okay, so we got another critical number then. Because of that, we know that y prime is undefined at x equals 0, right? Okay, so we can go back to our table and we can add the value at 0. The first derivative is undefined. Okay, well, so is the second derivative, right? So can I apply the second derivative test there? I can't apply it, can I? Okay. So what do I have to do then at that first, if the second derivative fails? Once again, they screwed up my board. Second derivative test fails, so what do I have to resort to then? First derivative, okay? Okay, so I need some test values, don't I? Okay. Well, I could use those values if I wanted to, right? I've already got them on my table. Those are kind of awkward ones to use, but that's all right. We could take our first derivative and we could evaluate the sign. Those are a little strange. Let's pick values a little bit easier. Let's pick something like, how about like negative 0.1 and positive 0.1? So if I evaluate my first derivative at positive 0.1, for example, what am I going to get? I'm going to get 2 divided by the cube root of 0.1 minus 2 times 0.1. We don't have to use a calculator on this. We could, right? We could evaluate this with a calculator. Do you see a way that we could maybe kind of reason through this? What's the cube root of 0.1 going to be? Is it going to be a fraction? Talk to me about that. Cube root of 0.1. I don't want an exact answer. It can be greater or less than 0.1. Yeah, okay, keep in mind that like 0.1 squared would be 0.01, right? Does that make sense? So a cube root is going to have to be a number that's greater than 0.1 because I'm going to take the number times itself and times itself again and get 0.1. So it's going to be a number bigger than 0.1. So 2 divided by a number bigger than 0.1, but still it's going to be less than 1, isn't it? Everybody agree? So that's going to give me something, this term is going to be bigger than 2, isn't it? Everybody agree? That makes sense? I'm going to have 2 divided by some decimal between 0.1 and 1. And maybe we can just think about it as some positive decimal that's less than 1 even. If I divide 2 by a decimal that's less than 1, I get a number bigger than 2. minus 2 times 0.1, well, that's pretty small, right? Okay, dividing by a decimal is going to give me a bigger result than multiplying by a decimal less than 1, agreed? So what's the result going to be then? What's the sign going to be? It's going to be positive, isn't it? Okay, so we know that here we've got a positive. Okay, what about at negative 0.1? What about at negative 0.1? What's that going to give us? So a cube root of a negative is going to be negative, isn't it? Right? So I'm going to get 2 divided by a negative decimal. That's going to give me a big negative number. Not big, but it's going to be bigger than 2, right? I'm going to get a negative number that's going to be less than negative 2. Negative 2 point something or negative 3 or something like that. Minus 2 times negative 0.1. So that's going to be adding 0.2. So I got a relatively big negative plus 0.2. What's the result going to be? It can be negative. Okay, so then what's this telling me? What's going on at this critical number? What is the fact that the first derivative is undefined? What's that telling me about the shape of the extremum? If the derivative was 0, we had a horizontal tangent, right? Which led to a smooth feature, a smooth extremum. If the first derivative is undefined, what kind of shapes did we get for our extrema in that case? It's going to be a sharp corner, isn't it? Right? So we know it's a sharp corner going from a negative derivative to a positive derivative. So what's that going to look like then? What's that going to be? It's going to be a sharp valley, isn't it? Right? I'm going from decreasing to increasing, so it's got to be a sharp valley. Okay, everybody agree? Okay, so then what about, we could start to connect some dots here, couldn't we? Okay, well, actually, we still need to know what's going on with this guy, don't we? Okay, we've got this 0 of the second derivative. Okay, it's undefined. The second derivative is undefined at 0, but we need to check some point to the right of this 0 to see what the second derivative is, to see if it changed. Okay. Well, we picked negative 0.1. That's a number between 0 and negative 0.439. So let's evaluate our second derivative at negative 0.1. Okay, so if we do that, here's our second derivative. This is factored. What's that going to give us? Negative times, that's always going to be positive, isn't it? Right? So I'm getting negative there. So that's not an inflection point, is it? Everybody agree? To be an inflection point, it would have to transition in sign, the second derivative would. It doesn't do that. I'm going to find the same thing at 0.1, aren't I? Right? I'm still going to get, that's always positive, that's negative. And so there is no inflection point there, right? And so I could graph this thing. What are we going to get? The shape of this thing. And I don't want to spend a lot of time on this, but we've got a sharp V, we've got a rounded peak and a rounded peak. So isn't it just doing something like this? Right? Something kind of like that. We agree? Okay. And we could plug in 0 and -1 and +1 and find the coordinates, right, of those points if we wanted to. Okay. All right. Last one. I wanted to do one with, oops, wrong way. I wanted to do one with a trig function. Okay. And then we'll move on from this. Okay. So there's our function. Are there any places where this function is undefined? We got to find the domain. I don't know about you guys, but I don't remember where cotangent is undefined or tangent or secant or cosecant. I always think of those in terms of sines and cosines, right? It seems like that's easier. So if we take the 2x part is fine, right? No issues there. But the cotangent x term is going to have some problems because that's a fraction. That implies cosine over sine, right? So it's really the sine x that's causing the problems, isn't it? The zeros of the sine function would be the places where the cotangent function would have to be undefined. Agreed? Okay. So let's think unit circle then. Where is our sine function undefined? Is sine, does that correspond to the x coordinate or the y coordinate of places on the unit circle? The y coordinate. Okay, so where would the y coordinate be 0? There and there, right? Agreed? Okay, so those are the places there. See, this is one of the things I can't draw a dot anymore. It wants to do something. I don't get this. Won't let me do it. As soon as I try to draw a dot, it does something bizarre. I don't know what I'm going to do about that. I guess I'm just going to cheat and do this. Oh, what'd that do? Yeah, that's probably right. Okay, so those are the places, right? Those are the places where it's undefined. So how could you describe those? This doesn't give us any constraints on, it doesn't say between 0 and 2 pi or anything like that. So how would I say that? Say it again. Somebody heard some whispering out there. I can't tell. We got masks on. Pi n. Okay, yeah, like n pi, where n is an integer. Could be 0, could be pi, could be 2 pi, could be 3 pi. Could go the other way. 0, negative pi, negative 2 pi if I go backwards, right? Okay, so the zeros, the zeros of the denominator, so the places where the function is undefined, are n pi. Okay, what are those going to look like on our graph? What's going to be happening at those places on our graph where the function's undefined? Okay, how come, Seth? You're right. Okay, you're right, but I want you to defend that. Tell us why would those have to be vertical asymptotes? You're right. We know we have vertical asymptotes in a cotangent function, but in terms of this ratio up here, how do we know those aren't holes? How do we know those are vertical asymptotes? Okay. Okay, good. So in other words, n pi, those are going to be unique zeros of the denominator, right? There's zeros of the denominator, but not the numerator. And so that means vertical asymptote, right? Okay, so we got a bunch of vertical asymptotes. Good. Let's take derivatives. How about our first derivative? What do we get? Derivative of 2x is 2. What's the derivative of cotangent x? Now, come on. I know you're rusty, but what is it? We might need a little derivatives quiz to force you guys to remember this stuff. It's negative cosecant squared, right? Remember, the derivatives of the co-functions are always negative. The derivative of the regular trig functions are positive. So we're getting a negative cosecant squared x, okay? All right, let's find the zeros of that first derivative. So would you guys agree here that, that y prime equals 0 when cosecant squared equals 2, right? Okay, cosecant squared is just 1 over what? Cosecant's the reciprocal of Sine, there you go. So 1 over sine squared x equals 2. In other words, if I solve that for sine x, I'd flip this thing and get sine squared x equals 1/2. So what are my solutions then? Sine x equals what? Well, I'm square rooting. I'm not squaring. No. If I square root both sides, I get sine on this side. What's the square root of 1/2? I got to have a plus or minus, don't I? Because I'm square rooting both sides. So 1 over the square root of 2. We're more, we would probably rationalize that, multiply top and bottom by radical 2, and get square root of 2 over 2. Everybody agree? Okay. Those are places we know on the unit circle, aren't they? Right? Where does sine equal plus or minus the square root of 2 over 2? Well, I know that's a place right there. Oh, I can't do that, can I? There's a place right there. Come on. There's a place right there, right, where the sine equals square root of 2 over 2. There's a place right there where the sine equals square root of 2 over 2, or, yeah, positive, right? Down here is where it equals negative and negative. Agreed? Okay, and we know I don't really care about the x coordinates, but these are places, once again, oh, I'll do that. Okay, right, so I got those 4 places. What are those angles? Pi fourths, 3/4 pi, 5/4 pi, 7/4 pi. I could go backwards, negative pi fourths, negative 3/4 pi. So how would I describe those? Okay, something like that. We're going to have to turn it into something like that, but without even being too fancy, what are those having? What do they sound like? Pi fourths, 3/4 pi, 5/4 pi, 7/4 pi. Those are what kind of multiples of pi fourths? Pi fourths times 1, 3, 5, 7, 9. What do those all have in common? They're odd. Those are odd multiples of pi fourths, right? So I get critical numbers then. What does that amount to? I get critical numbers at odd multiples of pi fourths. How do I say an odd number? If n is an integer, we already established n was an integer, right? We said we used n. We had vertical asymptotes at n pi. So how do I say an odd number if n represents an integer? 2n plus 1 or 2n minus 1, doesn't matter. Same thing, right? Okay, so I'm going to do that. 2n minus 1 times pi fourths, right? Agreed? That's odd multiples of pi fourths. So that's all the critical numbers. Okay, that's a lot of critical numbers. We're not going to be able to write them all in, but when we build our table, oh, that's bright. When we build our table, what do we got here? We already know, I'm not going to be able to get all of them, but I know that we had undefined places at n pi. So that's 0, pi, 2 pi, etc. Right, I've got all those places where the function's undefined. This is going to get, it's going to start to get really messy up here, isn't it? Because we've got so many critical numbers between 0 and 2 pi, we had 4, right? Let's spread this thing out a little bit, first of all. In fact, let's just look. Okay, we'll pick this up. Oh, so how's this going to work, right? You guys, in calculus, we're not always going to go twice a day, every day, but today we are. You don't have to be here, though. For the second part, it'll just be online. I don't think, actually, you can't be here anyway. I don't think you can't, so it's not an option. So you guys will be online if you can, if you're working or you can't make it or something. I'll record it, of course, and put it up there. Okay. All right. Have a good one. See you guys. So the PM version is at 1:56 to 2:36. That's when I'll be live. But once again, you guys don't have to be here live. If you can't make it live for some reason, I'll record it. Okay, but it would be advisable to be here.
You said it was at 1:15.
1:56. 1:56. Yep, you got it. Oh, I have assigned seats. Yep, let me get you going here. Okay. All right, give me a second. Okay. What is this doing?